Welcome to today's session. Today we are embarking to our second session to the topic more concept, stoichiometry, and formulae. For those who have not yet watched the previous session, let's go back and we on the channel and we go through that session and then we continue with this. In this session, we shall be looking majorly at stoichiometry in calculations under the more concept. And now the question is, what is stoichiometry? So we're saying stoichiometry is the part of chemistry that deals with the quantitative relationships between reactants and products, in a chemical reaction. So when we talk about quantitative, we are looking at how much the relationship between the how much we have for reactants and also the products in any given chemical reaction. And they're saying that it is based on the mole concept, which helps chemists determine how much of substance is involved in a reaction. Let's consider this balanced equation for formation of ammonia. We see nitrogen reacts with hydrogen to produce ammonia gas. So in this case, we are saying that ammonia is the product. When you look at this equation, what is on the right hand side is what we call the product, and then on the left hand side is what we call the reactant. So in this case, we are saying ammonia is the product. So ammonia is a product, and hydrogen and nitrogen are called reactants. So reactants are those substances we find on the left hand side. Like now we have nitrogen and hydrogen, while on the product side we have ammonia gas. The question is, what indicates that both reactants and products are gases? So we can see we have these subscripts here, states, where we have G, even here we have a G, and even here we have a G, showing that nitrogen is in gaseous state, hydrogen is in gaseous state, and then ammonia is also in gaseous state. And now we have these values, the ones we call the coefficients. Here we have coefficient 1 for nitrogen. You can look at nitrogen here. Its coefficient is 1, but we don't write 1 because it is just silent. Therefore, we may not be seeing 1, but 1 is always there, but silent. Then we have 3, the coefficient of hydrogen, which is 3. When you check here behind what is on the left hand, the number which is on the left hand of any species of any substance is what you're calling the coefficient. And in this case, when you look at hydrogen, the coefficient of hydrogen is a 3. So all these values, the 1, the 3, are called the stoichiometric coefficients. And similarly, we are saying the coefficient for ammonia gas, this one which is on the product, its coefficient is this 2. The coefficient is 2. Stoichiometric coefficient, it shouldn't be something that disturbs our minds every time we talk about stoichiometry things. When you talk about stoichiometry, we are just looking at the relationship between how much reactants are producing how much of the product. And if we know how much product is produced, then we can be able to know what reacted to produce the product. And we are saying that we can do that when we are having a balanced equation. In senior 2, we looked we were able to look at balancing equation and writing chemical formulas. We shall be able to go through it again in our next session. Make sure that you be alert when on the next session we shall be looking at also that for balancing equations and also forming the chemical formulae of different compounds. So saying in this stoichiometry, we have to make sure we have a balanced equation. And these values that we use to balance are the ones we're calling the coefficients. And the name given to these coefficients, these values, is what we call the stoichiometric coefficients. Okay. Now, we're saying that these coefficients, the 1 for nitrogen, the 3 for hydrogen, and the 2 for ammonia, these coefficients represent the number of moles taking part in a given chemical reaction. And we're saying that balanced equations are useful when predicting the amount of reactants used or products formed. So the coefficient that we're talking about, the 1, it means when you interpret this equation in terms of moles, we can use the coefficients, the stoichiometric coefficients, to interpret this equation in terms of moles. And in this case, we can say 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. So we are saying that the coefficients represent the number of moles, and we're going to see how best this is going to help us as we carry out the calculations involving stoichiometric calculations in mole concept. We are going to have different examples, and we see how best we can apply that in doing all these calculations. Let's look at the first example. So the first example, we're looking at converting mass to mole and also mass to mass calculations. So in this case, we're saying to convert between mass and moles, and then we use also the molar mass. In the previous session, we looked at how to determine molar mass of different elements, and we said the molar mass of any element is given on the periodic table. So we can always check on the periodic table, we check on the molar mass of different elements. Then if we are talking about the molar mass of a compound, we're able to see how to calculate the molar mass of a given compound. We shall be able to see, reminding ourselves on how we can calculate molar mass of calcium carbonate, of calcium oxide, of any other compound that you have. All that we shall be looking at it in this session, but also we have a full session in the previous session we had, where we looked at calculating relative formula mass and also calculating the relative molecular mass plus relative atomic mass. So we can still use that session and that video tutorial to go through the calculations of molar mass. Let's look at the first example. The first example says calculate the mass of calcium carbonate required to produce 4.4 grams of carbon dioxide in the reaction. So as we recall, we say that stoichiometry, it helps in calculating the quantities, showing the relationship between the products and the reactants. Now, in this case, we have calcium carbonate decomposing to form calcium oxide and carbon dioxide gas. Now, the question is, how much of calcium carbonate decomposed to produce 4.4 grams of carbon dioxide gas? So we can answer this question very well using what you call stoichiometry. And if you recall very well, we say that the coefficients of different substances, their coefficients are the ones we call stoichiometric coefficients. And you can get to know the stoichiometric coefficients after balancing the equation. We have this equation, calcium carbonate forming calcium oxide and carbon dioxide gas. Is this equation balanced? Let's look at it very well. So on the left hand side we have calcium, one atom. On the right hand side we have one atom of calcium. That is good, balanced. Then carbon, we have one atom on the left hand side and one atom on the right hand side. So we say that one is very balanced. When we look at oxygen, it has a subscript here, a 3, meaning there are 3 atoms of oxygen. Then on the right hand side, oxygen is distributed in different substances in calcium oxide and carbon dioxide gas. In carbon dioxide, oxygen you have 2 atoms. You can see the subscript here. And then in calcium oxide, there is 1 oxygen atom. So when you add this 1 oxygen atom here, plus the 2 oxygen atoms in carbon dioxide gas, they become 3, which means that this equation is very well balanced. So if you find that the equation is balanced, that is good. So let's look at the solution and we see how to begin attempting this question. So in the solution, we have only 2 steps that we follow in calculating such. So in this case, we are saying that we know how much carbon dioxide is produced, but we don't know what they used, what was used, the calcium carbonate that decomposed to produce this carbon dioxide gas. So what do we do? The first step is write a balanced equation. Already we have seen that this equation is very balanced. So after balancing the equation, our next step is to interpret the equation in terms of moles. And now that the question is about mass, so we can also interpret the equation in terms of mass. We recall in the previous session, we were able to look at how the relationship between moles and mass, between mass and moles. So we're just applying the knowledge we learned in the previous session. Please, those who have not yet gone through the previous session, have time, go through it, and this session will become more enjoyable. And for those who have joined us for the first time on this channel, don't forget to subscribe, like, and share. And whenever you have any question, just press it in the comment section so that I'll be able to, of course, respond to those questions at any time. Yeah, so the first step, write a balanced chemical equation. So this is already balanced, and then after that, we interpret in terms of moles and also in terms of mass. Why in terms of mass? It's because our question is generally about mass. How much of calcium carbonate decomposed to produce this amount of carbon dioxide gas. So coefficients, we say that coefficient of these substances, the stoichiometric coefficients, they help us to know the number of moles. We have talked about it. And since the coefficient of calcium carbonate is 1, it means that 1 mole of calcium carbonate decomposed to produce coefficient of calcium oxide is 1, which means it is 1 mole of calcium oxide and 1 mole of carbon dioxide gas. Now, we recall that 1 mole of any given substance is equal to its molar mass. We looked at that also. Now, on the side work here, I have calculated the molar mass of different substances. One for calcium carbonate, one for carbon dioxide gas, and then the one for calcium oxide. So when you come back here, we see it is 1 mole, and 1 mole is equivalent to its molar mass. So we can calculate the molar mass of calcium carbonate, and it is here. Calcium carbonate, we use the molar mass which you can get on the periodic table, the molar mass of calcium, which is 40 times 1. Why 1? Because we have 1 atom of calcium. Then plus 12, which is the molar mass of carbon, times 1 because we have 1 atom of carbon. Then plus 16, which is the molar mass of oxygen, times 3, which is representing the 3 atoms of oxygen. So when you add 40 plus 12 plus 16 times 3, you get, what do you get there? 48. So 48 plus 12 plus 40, you are able to get 100 grams per what? Per mole. Each mole of 1 mole of calcium carbonate, it weighs 100 grams. We looked at that. So you can put 100 grams. We have not added anything, we're just interpreting the equation. So whenever you get such a question, what you need to do is to interpret the equation. And when you interpret it, you make sure you're keen on what is given. What is given in this question is only mass. So when we're interpreting, we interpret it in terms of moles and mass. We shall look at other various examples which involve other things apart from the mass. Then for carbon dioxide, you do the same and you get 44 grams. Calcium oxide, you do the same, you calculate the molar mass, which you get as 56 grams per mole. So we come and we feed in here. 1 mole of calcium oxide weighs 56 grams. 1 mole of carbon dioxide gas weighs 44 grams. Now, in the question, they are asking calculate the mass of calcium carbonate. So we are calculating the mass. Since we are calculating the mass of calcium carbonate, we don't know which calcium carbonate composed. Then, because calcium oxide is not our emphasis, we are going directly to carbon dioxide, because in the question, we are talking about calculate the mass of calcium carbonate required to produce this of carbon dioxide. So which means our main emphasis is on calcium carbonate and carbon dioxide gas. That's why in this case here I put the question mark. This is what we're looking for. And then carbon dioxide, they said it was what was produced is 4.4 grams. So after this step, we can interpret. Let's look at our second step. Second step is saying interpret the equation in terms of mass as follows. We're saying 100 grams of calcium carbonate decomposes to produce 44 grams of carbon dioxide. I believe that is clear. Just it is coming from there, where we are saying that from here, the way you could have said in terms of moles, 1 mole of calcium carbonate decomposes to produce 1 mole of calcium oxide and 1 mole of carbon dioxide gas. Now in this case, since our emphasis is on mass, that's why we are saying 100 grams of calcium carbonate decompose to produce 44 grams of carbon dioxide gas. We are not talking about this guy, the calcium oxide. Why? He is not our major point of emphasis. Our major point of emphasis is on carbon dioxide and is also calcium carbonate. So we are saying that 100 grams of calcium carbonate composes to produce 44 grams of carbon dioxide gas. Now, let's look at this. Do you know that we can interchange this statement and we start with the 44 grams? Why are we starting with the 44 grams? Because in the question, what is given, when you check in the question here, what is given in the question is, let me look at this. In the question, what is given is carbon dioxide, the mass of carbon dioxide that is produced. Therefore, it's better when we are interpreting, we start with carbon dioxide. That's why in this case, when you check here, in this case, the first statement, I have interchanged it, this statement here. It has been interchanged, and then we are saying 44 grams of carbon dioxide are produced by 100 grams of calcium carbonate. So this statement here is the same as the first statement. So those two statements are the same. Just what has happened is interchanging what was coming at the end. Now it comes at the beginning. Why? Because of the question that we have. Now, if 44 grams of carbon dioxide are produced by 100 grams of calcium carbonate, what about for 1 gram? Which means 1 gram of carbon dioxide is produced by, we divide 44 on both sides to leave here 1. So when you divide by 44 both sides, it means to be 100 divided by 44 grams of calcium carbonate. Now, in the question, it told us that it is 4.4 grams of carbon dioxide that was produced. So if 1 gram of carbon dioxide can produce this, what about 4.4 grams? So which means 4.4 grams will be this value for 1 gram times 4.4 grams. And finally, we'll be able to get our answer as 10 grams of calcium carbonate. And then you can conclude and say, therefore, 4.4 grams, this is G, please, okay, 4.4 grams of carbon dioxide are produced by 10 grams of calcium carbonate, and then you get your score. So this one is very good. You get your score there, you get your score there, and we also get our score here on interpreting the equation. So that is how best we could go through that question. And in that question, we are looking at mass to mass, mole to mass. We could see that is involving moles and is also involving mass. Let's look at part B. Part B, we want to look at the relationship between volume and mass. And we have this question here. This question is saying, calculate the mass of calcium carbonate required to produce 44.8 liters of carbon dioxide gas at STP. In our previous session, we looked at this molar gas volume. And when we're looking at molar gas volume, we found out that 1 mole of any given gas occupies a given volume at standard temperature and pressure. And depending on the temperature and the pressure, either it can be at room temperature or at standard temperature and pressure, you find out that this gas occupies different volumes. Now, in this case, saying that at STP, 1 mole of a gas occupies a given volume at STP, and we can still go back and we check, though we need to have this in our head. What does 1 mole of a gas at STP occupy? What does 1 mole of a gas at RTP occupy? RTP, we are saying it is room temperature and pressure. So when you're given such, if you look at this question, by the way, almost similar to the previous, but the difference is that in the first example, we had mass of carbon dioxide, but in this case, they have given us the volume of carbon dioxide. So how can we relate the mass? Because they want us to get the mass of calcium carbonate, which is required to produce this volume of carbon dioxide gas. So what do we do? So the first step is to write still the balanced equation. So when you write the balanced equation of calcium carbonate, which decomposes to form calcium oxide and carbon dioxide gas, we said that in this case it is already balanced. The coefficient here is 1, the coefficient here is 1, the coefficient here is 1. Therefore, in terms of moles, this is 1 mole of calcium carbonate decomposes to produce 1 mole of calcium oxide and 1 mole of carbon dioxide gas. But we say that 1 mole of calcium carbonate, it weighs 100 grams. 1 mole of calcium oxide, it weighs 56 grams. Now, when you go to carbon dioxide, we don't consider the mass. Instead, in this case, we consider what 1 mole of a gas occupies at STP. And if you check very well, 1 mole of any given gas at STP occupies 22.4 liters. Now, they're asking, what is the mass of calcium carbonate produced required? That's why you have put a question mark. This is what is required. Is required to produce 44.8 liters of carbon dioxide. So after having this, we can just interpret this equation as follows, and we say 22. Why are we starting with these liters? Because is what we are given already. We are given what has been produced as 44.8 liters of carbon dioxide. So since we already have this produced, which means now we can start with the one which you already have. So we can say 22.4. We start from here. We start from here because this is the interpretation of this equation in terms of now the liter and in relation with mass. So we're saying that 22.4 liters of carbon dioxide gas are produced by 100 grams of calcium carbonate. So 22.4 liters of carbon dioxide are produced by 100 grams. Now the question is, where are we leaving the calcium oxide? The calcium oxide is not being included. Why? Because it is not inclusive. It is not part of the question. So because it is not part of the question, that's why we eliminate or we ignore it at this case, and we consider only calcium carbonate. We only consider the carbon dioxide gas. So after that, if 22.4 liters of carbon dioxide gas are produced by 100 grams of calcium carbonate, now the question is, what about 1 liter? What about 1 liter of carbon dioxide gas? Now 1 liter of carbon dioxide gas is produced by, we divide by 22.4 liters. We divide by 22.4 liters both sides so that we can remain with only 1 liter. So which means in this case we have 100, the volume. In this case we have 100 divided by 22.4 grams of calcium carbonate. Now, if 1 liter of carbon dioxide is produced by this, then what about the 44.8 liters? Now, this is the liters which they have given us here. If 1 liter can be produced by this of calcium carbonate, then what about the 44.8 liters? So it will be 100 over 22, this over 22 times the 44.8 liters. So the answer we get 200 grams of calcium carbonate. So we can conclude and say, therefore, 44.8 liters of carbon dioxide are produced by 200 grams of calcium carbonate. And you get your score. You get your score. You get your score. You also get your score. You can see you can get 4 scores there. So that is, you can see this one was involving volume. You can see it is involving volume and what? Mass. Why? Because it is what was required in the question. Let's look at the last example. After giving you this last example, please go through the practice questions, which I'm going to give you practice on your own, and then you can submit your solution in the comment section, and we see how far you have gone in regard to this topic, more concept, stoichiometry and chemical formulae. Our last session, we shall be looking at chemical formulae and balancing equations. we are going to have a recap. I know we have ever done this, but we shall be looking through that so that we can remind ourselves on how best we can balance equations, on how best we can form chemical compounds and chemical formulas of different substances. Let's look at this last example. So this last example is saying ammonia is produced in large scale by Haber process. Calculate the volume of ammonia produced at STP when 300 cubic centimeters of nitrogen was reacted. So in this case, they want us to calculate the volume of ammonia which is produced. Very good. So the first step, write the balanced equation for the reaction. Write a balanced. There is a what? There is a D here. So please make sure that you put a what? Write a balanced equation for the reaction. So we have nitrogen reacting with hydrogen to produce ammonia. But we have put these coefficients. Are you seeing them? The coefficients are here. Now, coefficient of nitrogen is 1. We said 1 is always silent. Therefore, you may not see the 1. So, these coefficients are the one we call stoichiometric coefficients. Now, stoichiometric coefficient of nitrogen is 1. 1 for hydrogen is 3. Coefficient of ammonia is 2. So, when interpreting in terms of moles, we have to say 1 mole of nitrogen reacted with 3 moles of hydrogen to produce 2 moles of ammonia. Now, after the reason why we start with a mole is because a mole can relate us with a mass. We can relate a mole with volume. So that's why we always start with a mole. And I believe this is the best, simplest formula that we can use when we are calculating such questions. Now, let's look at this. We say that 1 mole of a gas at STP, don't forget, this is at STP. What does it occupy? Now, in this case, our volume is in cubic centimeters. We have to be very inquisitive, and we have that understanding that these volumes can be converted from liters to cubic centimeters, from cubic centimeters to liters. We looked at that in our previous session. As I said, those who have not yet gone through our previous session, let's go back and we go through it. All that has been explained there under molar gas volume. So we say that 1 mole of a gas at STP occupies 22,400 cubic centimeters. The reason why you're using cubic centimeters, because even now question you have it in cubic centimeters. Now, if 1 mole of a gas occupies this, what about the 3 moles? It will be 3 times 22,400 and you'll be able to get 67,200. What about the 2 moles? It will be 2 times 22,400 and you get 44,800 cubic centimeters. So don't start worrying, where did this one come from? Where did this one come from? It is from the other statement said 1 mole of a gas occupies what? At STP and in these units cubic centimeters. So it occupies 22,400. What about the 3? And by the way, we didn't put the state symbols, but we said that ammonia is in a gaseous state. It is in a gaseous state. Please make sure that you put these symbols. This is gaseous. You write this. I don't know how to write it very well here. I will have it like this. Good. So we have also this. I'll just write it like that. There it is also in a gaseous state. All these are gases, and you say that all gases occupy by using what you call the Avogadro's principle and Avogadro's constant. But in this case, Avogadro say that 1 mole of a gas occupies the same volume, they occupy the same volume at standard temperature and pressure. Now, after interpreting that in terms of volume, look at what we have been given. They have said that 300 cubic centimeters of nitrogen. Yes, is the one which reacted, and they want us to know how much ammonia gas has been produced. That's why you have put a question mark. After that, we interpret the equation. Because when you're answering, you don't need to write for us these steps. We're just showing you these steps so that you can know them for this example. But when you're doing your exam, don't show the steps. You can just follow the steps very well, but without writing all this. This one is for the case of our learning. Now, step 2, we interpret. Now, what are we interpreting? The volume. This one, you call it is interpreting the equation in terms of volume. And don't forget, our major emphasis is on nitrogen, and our major emphasis is on ammonia. Hydrogen, we don't have what to do with hydrogen. That's why when we are interpreting, we are looking at the units of nitrogen and the units of ammonia. So we're saying that 22,400 cubic centimeters of nitrogen reacted with hydrogen gas and produced, or to produce hydrogen gas produced 44,800 cubic centimeters of ammonia. Where is it coming from? It is here. 44,800 of ammonia. If this produced this, what about 1 cubic centimeter? So you can say 1 cubic centimeter of nitrogen reacted with hydrogen gas and produced 44,800 cubic centimeters over 22,400 cubic centimeters of ammonia. Are we there? Then we continue. What about if 1 cubic centimeter can produce this? This one should go off. This one is not there. This one is not there because we are dividing by only 22,400 both sides, not 22,400 cubic centimeters both sides. So make sure that this is not there. So even here we also cancel this. It is not supposed to be there. Now we are saying that if 1 cubic centimeter of nitrogen reacted with hydrogen gas and produced this, what about 300 cubic centimeters of nitrogen? It reacted with hydrogen gas and produced 44,800 over 22,400 times 300 cubic centimeters of ammonia. So when you do your calculations using your calculator, you find that you get 600 cubic centimeters of ammonia. So that will becomes our answer. Please make sure you always pause and you get this concept very, very well. So you get your scores. Please don't forget, those who have not yet subscribed, please don't forget to subscribe, like and share. If this has been helpful, comment and like and subscribe. Don't watch and then if you have been with us up to this time, don't forget to subscribe and help our friends also to gain from what we are getting. Now, these are practice questions. These practice questions are yours. They are only 2 numbers. Have time and go through them. Pause. I'm not going to read each of them, but what you're going to do is to go through these numbers. They are only 2 numbers. Go through them, do them, follow the work that we have already discussed, and then at the end of it all, you can submit your solutions to the comment section, and then we keep on discussing on the comment section. But also, you can also inbox if there's anything which is hard for you that you have failed to interpret very well. You can inbox on this number. It is very well written here. Inbox on that number, and any number. It's all these numbers on WhatsApp. We can be able to link up, or you can share an email address. You can have a plan, and then we meet online, and then we see how best we can solve some of the questions and some of the challenges that you're getting. I continue to remind us not to forget to like, comment, and share, and also subscribe for more videos like this. Otherwise, have a blessed time. Let's meet in our next session as we wind up with this topic of mole concept, stoichiometry, and chemical formulae. If you still have any query, any question that has been disturbing you at any point, don't forget to share that question, and then we see how best we can work with it and also deal with it. Otherwise, have a blessed time. God bless.